And finally, let's take a look at one of the results from the performance measurements that are shown in the Anderson's paper. This is figure 3 from that paper if you're following along. This figure shows measurements that were gathered from executing a program with multiple processes, and each process executed a critical section. The critical section was executed in a loop 1 million times. The number of processes in the system was varied such that there is only one process per processor, and the platform that was used was sequence symmetry that had 20 processors. So that's why the maximum number of processes was also kept to 20. Also, this platform was cache coherent with write invalidate. The metric that was computed based on the experiments was the overhead that was measured compared to a case of ideal performance. An ideal performance corresponded in these measurements to a theoretical limit how long it takes to execute that fixed number of critical sections. So basically, if there is no contention, no effect due to the fact that each of these critical sections needs to be locked and unlocked, then how long would it take to run these number of critical sections? The measured difference between that theoretical limit and whatever it actually took to perform this experiment was considered the overhead, and this is what these graphs represent. These experiments were performed for every one of the different spin lock implementations we discussed, from the spin on read, the test and set, all the way to the queuing implementation. These results don't include the basic test and set when we're spinning on the atomic instruction. Basically, that implementation would result in something that would just completely be off the charts. It would be the highest overhead, the worst performance measurement. And then notice how we have, for the different variations of the delay, both the static and the dynamic delay. So let's see what happens under high load. This is where we have lots of processors and lots of processes running on those processors that are contending for the lock. We see from these measurements that the queuing clock, it's the best one. It is the most scalable, and as we add more and more processors, more and more load, it performs best. The test and set lock, that's this line here, that one will perform worst. That is in particular the case because here we have an architecture that's cache coherent with write invalidate. And we said that in that case, on release of the test and set lock, we have an order of n squared memory references, so a very high contention on the shared bus, and that's going to really hurt performance. Of the delay-based alternatives, we see that the static implementations are a little bit better than their dynamic counterparts. Since under high loads, with static, we end up nicely balancing out the atomic instructions, whereas with dynamic, we still end up with some randomness with some number of collisions. Those are avoided in the static case. Also note that delaying after every single memory reference is slightly better than delaying after the lock is freed only, so only on release, because when we avoid after every reference, we end up avoiding some additional invalidations that come from the fact that sequent is a write invalidate architecture. Under light loads, when we have few processes and few processors as well, we can make a couple of observations. First, we see that test and set performs really pretty well in this case, and that's because this implementation of a spin lock has low latency. We were just performing a check if lock equal busy, and then we were moving on to the atomic test and set. We also see that in terms of the delay alternatives, the dynamic delay alternatives, the backup delay alternatives, perform better than the static ones. And that is because with the dynamic alternatives, we end up with lower delay. We said that static alternatives can lead to situations in which the two processors that have the extreme, the smallest and the largest delay are the only ones that are contending on the lock, and so we have wasted cycles. We also see that under light loads, the queuing clock performs the worst. This is the performance of the queuing clock. And the reason for that is we explained that with the queuing clock, we have pretty high latency because we need to implement the read and increment and the modular processing, etc. So this is what hurts the performance of the queuing clock under light loads. One final comment regarding the performance results that we just discussed is that this points to the fact that with system design, there isn't really a single good answer, that the design points should be driven based on the expected workload, light loads, high loads, architectural features, numbers of processors, write invalidate, write update, etc. The paper includes additional results that point to some of these trade-offs in more detail.